we can start. So first of all, I forgot to tell you at the beginning about this book, which is in preparation. I gave you a preliminary version, and so if you find any mistake or typo or error of some sort, please let me know, because it's really useful at this point to fix the mistakes, okay? Okay, so now let's recapitulate what we did yesterday. So we are discussing now high-dimensional inference, where we want to infer many parameters, and many means of the order of the data we have. So we are in a regime where the number of parameters and the number of data are comparable. And the simplest example we can discuss is the case of Gaussian variables. So we considered Gaussian variables of size L. L is the length of our data. So if the data are, so we work under the assumption that the data are generated by a multivariate Gaussian with a matrix T that is a L by L matrix, symmetric and positive definite. So the true correlation matrix is the inverse of T. Okay, so this is our model, and we assume that we are given data generated from this model. So the data are M vectors, IID, generated from this, and we can collect them into a matrix Y, where each line is a data vector. So Y is going to be a matrix of size M times L, where M is the number of data. And so what we have seen is that if we do Bayesian inference, basically maximum likelihood inference, so we assume the same probability distribution, but with the matrix T that we want to find, what we obtain is that we should compute the empirical correlation matrix, which is just Y transpose Y divided by the number of data. And then the maximum likelihood estimator for T is the inverse of this matrix, okay? Now, what we have seen also yesterday is that the important parameter here is the ratio of the size of the problem, L divided by the number of data. And what we have seen is that when R is of order 1, the difference between C and C hat, or between T star and T hat, can be very large. Even if each matrix element is of order 1 over square root of M, the correction to each matrix element is of the order of 1 over square root of M, the impact, because there are many matrix elements, all these little mistakes can accumulate, and in the end, it can happen that the eigenvalues and eigenvectors of T star are very different from the eigenvalues and eigenvectors of T hat, which is a problem, because what we really care about are the eigenvalues and eigenvectors, because these are the parameters that characterize the distribution of Y. So we have seen this in a particular example where T hat, we took the simplest possible case where T hat is the identity plus a rank 1 perturbation, right? So S hat is a number and E hat is a unit vector. So we add to the identity a small perturbation in one direction. So our data, we assume that our data are basically, they all have the same variance in all directions but one, where the variance is a little bit here. Sorry, this is C hat, where S is bigger than 0, so the variance is a bit larger in one direction. So then we discussed this case, and what we found is that the maximum, so we want to estimate S hat and E hat, and we found that the maximum likelihood estimator in this case is, well, the analog of this means you have to your E star is the is the maximum eigenvector of C, where C is the empirical correlation. So you have to compute the empirical correlation, and you have to find the principal component, and S star is the maximum eigenvalue minus 1. So these are the best estimators, but what we have seen is that if R is too big, so if you have few data, or if S hat is too small, so what matters is the ratio between S hat and the square root of R. So if the signal is large and the noise is small, then you can recover the information. So S star is close to S hat and E star is close to E hat. But if the signal is small or the noise is large, so if you have few data basically, then the scalar product between E star and E hat is 0, and you cannot recover the signal. Okay, this is what we have seen yesterday. So you have a phase transition, and the phase transition happens in the limit where L and M are going to infinity with fixed ratio as a function of R. And you have two phases, one where you can infer the signal, and one where you cannot infer the signal. Okay? Is it okay up to this point? Now, what we want to do, what I wanted to do today, I will show you an application of this, but before I would like to discuss a different setting where you can do principal component analysis, but not in one shot as you do here, but in an online way. So suppose that now the setting is going to be a little bit different. So the same problem, so you have Gaussian variables, Gaussian data, with a certain T hat and a certain C hat, which are the true correlations of your data. And now, instead of being given a sample of M data altogether, you are given one sample at a time. Okay, this is called online learning. And so at each time, you are given one data, yt. Now let me follow the notations of the nodes. Yeah, we call this yt, which is one vector in R to the L that is drawn independently from this distribution. And you would like to learn something about the distribution that generated the data. So how can you do that? So what we want to do now is to just learn the principal component. And so you can do this in a very simple way. So let's consider a very simple neural network where these are the y, y1, y2, y3, y4, yl. Okay, so you show the data point to a network, and the network will compute an output. So there will be some weights, J1, J2, JL, and there will be an output Z, and the output is just J dot Y. Okay, so this is a perceptron. Essentially, you do a scalar product of J with Y with the input, and you have your output. So how can these weights J learn something about the data? So the idea is very simple. What we are going to do is to update the weights at each step. And the update rule will be this one. So J t plus 1 is going to be Jt plus a learning rate eta times z of t. So z of t will be j of t dot y of t, where y of t is the data point that you get at time t. At each time step, you get one new data point. Times y of t minus z of t j of t. Okay? So why we do this? What's the logics behind this? The idea is basically what you want to do. So you are trying to approximate, you have a simple neural network with only one output. So you are trying to approximate a vector by j. You are trying to approximate your vector with this j. And what you want to do is to find the j in such a way that y is as close as possible to z times j, right? Because if y is close to z times j, this term is small, and jt plus 1 is going to be jt. So you get a stationary state. The network should converge to a state where the network is trying to approximate the data by its own weights multiplied by z. And then you see if, now if I show you a new data point, yt, then you try to approximate it in this way, you compute z. And then basically if what you get, for example, if y is bigger than z times j, you will increase, and z is positive, you will increase a little bit the vector j to try to fit a bit better your data point. And if y is smaller, you will reduce a bit the weights, and if z is negative, it's the opposite. Okay? So intuitively, we would expect these kind of things to converge to something where the network is choosing some j's such that when you project your data on j, you get the best possible approximation. And this is the principal component. This is what principal component analysis is doing. Okay? So this is called online PCA. And so let's try to see if this works. Does it converge to the principal component?
Excuse me.
Yes?
Can you please repeat how we want to find j?
So we will start from some random j. Okay, let's say at the beginning we put some random j. Then at each time step, you receive a new data point, yt. So you update your j according to this rule.
Yeah, I know. I mean, I think I thought you said that we want to find j such that y would be equal to z dot j.
As close as possible, statistically as close as possible, yes. But so, okay, let's separate two things. So one is what we do, so the algorithm. The algorithm is very simple. You start from random j. At each time step, you are shown one data point that is different at each, you get a new data point at each step, you update your weights, and you keep doing this until you have data, okay? This is the algorithm. Now, I was trying to give some intuition for why this algorithm should converge to the principal component, but then I will show that it converges. But the intuition is that this thing, when you converge, it means that jt plus 1 will be close to jt. So this will fluctuate all the time, so it will keep fluctuating. But when you reach a steady state, this should be close. So this term should be close to 0, as close to 0 as possible. So this will be close to 0 if on average, y is close to z times j. So j should be such that if you project y on j, so z is the projection, j will be a vector. You project your data on j, you get a number. And now this number times j is as close as possible to y. And this means that you are trying to find a direction in the space of the data that maximizes the agreement between the data and the projection of the data on that direction. And this is the principal component. The principal component is the one that maximizes that captures most of the variability in the data. But this is intuition. Now we can do now we will do the mathematics, and we will see that this converges to the principal component. Okay? Okay, so to do that, so now we want to analyze this algorithm. And how do we analyze this algorithm? We can, okay, the data are generated in this way, but let's make some space. So in order to analyze this algorithm, we can take the limit. So then I will show you an implementation of this algorithm with finite L, finite M, finite number of data, finite learning rate, and so on. But to analyze the algorithm, we can take a limit, which is the continuous time limit. So we will take the limit where eta is going to 0. So we consider a very small learning rate. And then the time will become large in such a way that we will call tau eta times t. So we assume that we are doing many time steps. We have many data. And at each time step, we do a small change to our weights. So to see what happens, okay, first of all, let's put z here. So here we get j of t dot y of t. This is z. And here we get y of t minus z, which is, you can write it as j of t dot y of t times j of t. Okay, this is the same. I just put the definition of z. Now, what we do, we say, okay, if eta is very small, the change of the weights is going to be very small at each time step. So I can consider that the j's are almost constant in a single time step. And before the j change, there will be many time steps. So I can replace this thing by its average. Okay, I will average this over the data, because I assume that before the weights change, this thing, I will see many data, okay? So let's do that. So of course now jt plus 1 minus jt divided by eta in this limit is basically the derivative of j. So what we get is that the derivative of j with respect to tau, which is the time, right? So jt plus 1 minus jt divided by eta, which is this, will be approximated by the average. You can show that the correction to this is of the order of eta in this limit. Okay? I will not do it, but I think you can do it. So let's take the average of this. What is the average of this? I get j times y times y. So when I take the average of this, I get the average of y, which is c. Okay? So this will be c hat, which is the correlation of the data, times j, this first term. And in the second term, maybe if you want, I can write it here. So the average of, here I can write this as y times y transpose times j, this term, the product of this times this. And so this will be, j will go out of the average, and the average of y transpose is the correlation. So I get c hat times j. And this other term here will be y, j, j. So I get the average. This, I can write this as j times y. So j transpose times y transpose times j. So this is the scalar product of j with y, and this is y with j. So this and this. And then there is a j. So this will be j dot c hat dot j, because again the average of y transpose is c hat, times j, right? So my equation becomes derivative of j with respect to t is equal to c hat j minus j c hat j, which is a number. So this is matrix times vector, and this is a number times j. Okay? So, and j will be a function of time. And c hat instead is the real correlation of the data. Okay? So this is our equation of motion. Okay. Let's make some space and then I will write this again. So can I solve this equation? So first of all, what I can show, yes?
The term in the parentheses is just a scalar now?
Yes. This is a scalar and this is a vector. Okay, so now, first of all, I can show that if j is normalized to 1, it remains normalized to 1. It's convenient to have j normalized to 1 because, as I was saying, j is going to be some direction that will be the principal component. So if it is normalized to 1, it's convenient. So let's show this. This is easy to show. If you take the derivative of the sum of ji square, which is the norm of j, this is, well, you can put a 1/2. This is going to be sum over I of ji times the derivative of ji. Okay, and then I know here the derivative. Here, this is a vector, so I can put an I here if you want. Well, okay, this will be ij j with the sum over j. And this is a number, and here there is I. So, well, or actually, it's maybe better to, we can do it without the indices probably. It's probably easier. So this will be, sorry, without the indices, this is like this. This is the scalar product of j with dj over dt. And so you see that here we get j c hat j, which is a number, minus the same number, times j square, right? So if j square is equal to 1 at the beginning of the dynamics of this algorithm, then this is 0, and j square is not changing. So if you start with a normalized vector, it will stay normalized. Okay? So we will assume that J0 is random, but with unit norm, and then the norm will be 1 all the time. And then we can work now to see what happens. We can work in the basis where C is diagonal, okay? Because I'm analyzing the algorithm, so I'm assuming I know C. So if C is diagonal, this will become derivative of J, let's say K over tau, where K is the index in the basis where the matrix is diagonal. So this will become, if this is diagonal, this will be lambda jk. So lambda k jk minus this, if C is diagonal, is the sum over L of lambda L jl square times jk. Okay? So we get the derivative of j will be lambda k minus sum over L of lambda L jl square times jk. So you can solve this, and you can show. I mean, it's easier to check than to do it, but you can show that jk, the solution of this equation is that jk of tau is equal to jk of 0 times exponential of lambda k tau, normalized. So divided by square root of the sum over, let's say, L of jl of 0 square times e to the 2 lambda L tau. Okay? So this is the solution of this equation. So you see that now assuming that jk at the beginning is random, it will have some non-zero projection on each of the principal components of C hat. And this is jk of 0. And then each component is growing exponentially with a rate that is the associated eigenvalue. So what is happening is that the first component, it has the biggest lambda, so it will grow faster, and the others will grow slower. So at long times, when tau goes to infinity, the component J1 will become the biggest, but then it's normalized, so it will go to 1. So so J1 of tau will be equal to 1, and all the other j will go to 0 in the limit of, maybe I can write it. So the limit for tau going to infinity of J1 is going to be 1, and the limit for tau to infinity of all the other components is going to 0. So the algorithm is going to learn, so J is going to become the principal component of C hat. Okay? The rate of convergence, so the time it takes, is just the difference between the two, the first eigenvalue and the second eigenvalue. So the time it will take to reach the asymptotic limit is going to be of the order of 1 over lambda 1 minus lambda 2. Okay? Because this is the time over which exponential of lambda 1 tau is going to become much bigger than exponential of lambda 2 times tau. And then the other components are smaller, so this is the dominant. Okay? So what this calculation shows is that the algorithm I erased, maybe we can write it here. So the discrete time version is that j t plus 1 is equal to jt plus eta z of t times yt minus zt jt. So this is the discrete time algorithm, where z is the scalar product of y with j. So this is the algorithm you should run when you have finite data. But this analysis shows that when the learning rate is small enough and you have enough data, so if you have long time means many data, because at each time step you're getting a new data point, then this will converge to the principal component. So your network, this is still unsupervised. The network is taking this data as input, and it's doing something with the data at each step to update its weights. This will converge to the principal component. Okay? This is something that happens in many other kind of networks. For example, when you have autoencoders, in autoencoders, I don't know if you know what are autoencoders, but I mean, these are basically networks where you have, like, you show some input and you have some bottleneck, and you try to match the input and the output, introducing a bottleneck. And also in that case, what you can see is that these nodes, at least at the beginning, will learn something that is close to the principal components. Okay, so this is a very simple example where you see this kind of things happening. So in general, when you have machines that have some internal representation, at least at the beginning of the learning, these internal representations will tend to be close to the principal components of the data correlations. It depends then on the machine, but okay. So fine. This is a way to learn the principal component if you are given one data point at a time instead of having all the data at once. That can be useful in some cases. It's also interesting to observe that in this setting, it's also easy to add a regularization. So let's also discuss this. We haven't really discussed regularization up to this point. So maybe you can suspect that your data, that your principal component for some reason is sparse, or maybe you want to have a sparse principal component. And then you can say, okay, maybe I want my J's, I want the weights of my network to be sparse as well. So what can you do to make them sparse? So one standard way is to add some regularization. And a convenient regularization, a convenient compromise, I didn't really discuss regularization in this course, but I think you have maybe done it before. So a convenient compromise between having something that is tractable but that enforces sparsity is the L1 regularization. So L1 regularization means in this case that you are adding here a term minus gamma times the sign of J, T. Okay? Why? Because this is basically the derivative of J with respect to time, this thing. And so if you have a L1 norm, means you add the penalty to the loss function that is gamma times the absolute value of J. So when you do the gradient of that to get your gradient descent, the gradient of an absolute value is the sign. So this is telling you that when you update your weights, you add the penalty that is trying to keep the weights close to 0. So if the weights is positive, you put a minus gamma. If the weight is negative, you increase the weight. This sign is done component-wise, so each component. Okay. So if you, okay, so you can do this. You can add this penalty, and if you do that, okay, this is the implementation of the algorithm. When you want to analyze the algorithm, you can do exactly the same thing, and exactly the same procedure as before. We send the learning rate to 0. We assume that time is scaling as 1 over eta in such a way that the continuous time is finite. And you get this equation where you add minus gamma times the sign of J of tau. All the rest is the same, so you just have to add this term. So we can analyze what happens when we add this penalty. Okay. Okay, now the analysis is a bit more complicated because we cannot solve the equation explicitly in general. But what we can do is to go back again to the special, yes? No, exactly. So in this case, the norm is not going to be preserved. And we cannot solve the equation in general. So we have to see what happens. Exactly. So what we can do is to go back to the special case where C hat is equal to the identity plus S hat, E hat transpose. Okay? So we consider again the simplest case where we have the identity for the correlation plus there is one special direction which is the principal component, and we can try to see what happens in this case. So in this case, we can compute this thing. So this is going to be equal to, let's plug this here. So we get J plus S hat times E hat times the scalar product of E hat with J. This is when I put C hat here. And in the second term, I get minus. This is going to be the norm of J when I put 1 here. And then I get plus S hat times, here I get E hat j square, okay? Times j minus gamma sine of j. So you see that now the equation depends on two objects, the scalar product of E with j and the square of j. So let's call them q. So I will call q the square of j, which is not conserved now. So this will be q of tau, and I will call r of tau the scalar product between the principal component and j of tau. Okay, so now what I get is that the derivative of j with respect to tau is equal to, I have I have a constant term, this one, s times E hat times this, which is r. So this is this term, and then I have this term that depends on, that is proportional to j. So I have plus 1 here, minus q of tau, minus s hat r of tau square times j, minus gamma times the regularization. Okay? Now, still, we cannot really solve this in general, but what you can see from here is that j equal to 0 is a fixed point. So if I put j equal to 0, then r is equal to 0, because r is j dot e. Here I get 0, and I can say, okay, the sign of 0, I can say it's 0, which means basically that if all these terms are 0, I get dj over dt equal to minus gamma sine of j, which means if I try to make j a little bit positive, this will bring it back to 0, and if I try to make it a little bit negative, it will bring it back to 0. So j equal to 0 is a fixed point with the convention that sine of 0 is 0. So, okay, this is, yes?
So you say if we have a j equal to 0, you have r equal to 0 and q equal to 0. But the secondly, you have 1 here. Yes, sir.
Yes, but I have j here. So if j is 0, this is all 0. So j equal to 0 is a fixed point. So in that case, the network is not learning anything. J is 0. There is nothing. But now let's see if there is another fixed point where the network is learning something good. And so, unfortunately, I cannot, it's not easy to analyze this in general, but what we can do is to, well, okay, we can write this component-wise. So this is going to be EI. This is a number. This is JI. And this is going to be the sign of JI. So if we assume that this is positive, that we should check it later, but let's assume this is positive. If I look for a stationary solution, so I put the derivative to 0, and I look for a fixed point, if this is positive, what do I get? So if this number here, if this number is smaller than gamma in absolute value, then the only solution is j equal to 0, because if this is positive, okay, I always get, it's not easy to explain this, but now, so let's say if j is close to 0, this is small, and if this is smaller in absolute value than gamma, this term is still bringing you back to 0, and so the only solution is j equal to 0. So if S times E hat times R. I'm looking for a stationary solution, so R will be a constant. Everything is a constant right here, so I'm looking for a solution that is a fixed point. So if this term is smaller in absolute value than gamma, then the only possibility is j equal to 0. Otherwise, if this term is, for example, positive and bigger than gamma, there is maybe a sign that is wrong. That's why I'm getting stuck. Let me check the sign. No, the sign is correct. Okay. Yes. Because I want to. Yes. Yes. Wait. No, there is something. There is some sign that is wrong. I think there is a typo somewhere. Yes, there was a wrong sign. I'm sorry. No. Okay. I said things in the wrong way. I have to assume that this thing is negative. Sorry, not positive. Otherwise, it was wrong. So this should be negative. So let's assume that 1 minus q minus s hat r squared is negative. And then things work. So we will check later that this is the case. Sorry. So now if this is negative, then j should be equal to gamma times the sign minus this, divided by this. So if, for example, let's consider an example. If s hat is, if this is positive and bigger than gamma, then what do I get? J will be positive. I bring gamma on the other side. And then I get Ji is going to be equal to, here I get gamma. No, I get this S hat times E hat I times R minus gamma divided by minus this, because I bring this on the other side. Sorry, so I get Q minus S hat plus S hat R squared minus 1. Okay? And now this is positive if this is true. Okay? Is it clear? I'm sorry, I made a bit of confusion. So, yes?
In the first case, why did you put the absolute value?
Because, yeah, let's do the last case. If S hat times EI times R is negative, because the component of E hat can be positive or negative. So if this is negative and smaller than minus gamma, then here my equation is always 0 equal to this. So I bring now, I will have Ji. I assume that Ji is negative now. So this will be plus. And so I get the inverse. I get gamma minus okay, these things should be done. Let's make some space. This is 0 equal to S hat IR minus Q plus S hat R squared minus 1 Ji minus gamma times the sign. This is my equation, and this is positive. So now I bring this on the other side, this, and I get this positive number that I'm assuming to be positive times ji equal to s hat minus gamma. Okay? So if this is bigger than this, which is this case, I can assume that that J is positive. So this is positive. I get a positive thing, and this is positive, and it's okay. If instead this is very negative, more negative than minus gamma, then I can assume J to be negative. So this will be a plus, and J will be S hat E hat R plus gamma, because this is negative, divided by the same thing. Okay? So, and because I'm assuming that this is more negative than, this is smaller than minus gamma, this is negative. Okay? So if none of these two things are true, which is this case, you cannot find the solution, because if you assume J to be positive, it will be negative, and if you assume it to be negative, it will be positive. So that's why I put the absolute value. Okay? So if this is bigger than gamma, you get a positive J. If this is smaller than minus gamma, you get a negative J. And in between, so between minus gamma and gamma, you get 0. Okay? Sorry for the confusion. So this is our fixed point. And now we have to compute Q and R. So we get, because we don't know Q and R yet, so we have to impose this condition. But so now we can impose it, because now we know J, and Q must be the square of J. So Q will be the sum over I of Ji square, which is, now you can write, so this is your fixed point, J star. You can write this in a compact way. You can say that J star I is the sine of EI times the maximum between 0 and S hat EI absolute value R minus gamma divided by Q plus S hat R square minus 1. Okay, this is just a compact way to write this thing. So if, you see, if E hat is positive, you get this. And, I mean, if E hat is positive and this is bigger than this, you get this. Otherwise, you get the other two. So you can, maybe I will not rewrite everything here, but you can put this here, and you can write R equal to sum over I of E times Ji. So with J equal to J star, so in the fixed point. So you see that you get two self-consistent equations for R and Q. So you get Q as a function of Q and R, and you get R as a function of Q and R. Okay, but you cannot really solve this in general. So something you can do to see what happens, and then I conclude, is to consider a very simple case where the vector E, so the principal component, is sparse. So let's assume that the principal component is equal to 0 if I is equal to rho L to L. So there are a fraction 1 minus rho of the components that are 0. And the other ones, so for I from 1 to rho L, are non-zero. And because it should be normalized, let's say these are either plus or minus 1 over rho L, or 1 over square root of rho L. So this is a unit vector. Let's say this is rho L plus 1. This is a unit vector that has a fraction of the components equal to 0 and a fraction of the components that are non-zero and equal to plus minus something. So if you put this here, maybe I don't do all the calculations, but you get a simple result, because now all the absolute value of all the components is the same. So this is a very simple case. And what you get in that case from this is that Q is equal to R squared. And then you get an equation for R, which is R equal to S hat times R minus gamma square root of rho L divided by the denominator, which is R squared times 1 plus S hat minus 1. So now you get one equation for R. And what you can show from this equation, it's a simple calculation, is that if you plot R as a function of gamma, so you have you always have the solution with j equal to 0, which means R equal to 0, which is not here. This is under the assumption that R is non-zero. And what happens is that when gamma is small enough, you have a non-zero solution that will do something like this. And then it disappears at some point, and you have a first order jump to 0. Okay? So in this case, as a function of the regularization, what you get is that if the regularization is small enough, you converge to a solution that is proportional to the principal component. So J is proportional to E hat. So the system is able to learn the sparse component. And when you increase the regularization, at some point there is no solution anymore, and you get 0. You don't learn anything. Okay? So also in this case, you have a phase transition. Now this time it's as a function of gamma, of the regularization, between a phase where you learn and the phase where you don't learn. Okay?
Sorry,
yes?
the ratio between the values that are 0 and the not doesn't play a role here?
Yes, yes. The critical value of gamma depends on rho. So you can, because you see there is rho here. So the more, the more dense is the bigger is rho. There is the expression in the book. You can check. But the bigger is rho, and the smaller is the critical value of gamma, because the components are smaller. Yes.
I have a couple of questions. What is rho?
Rho is the fraction of components. So if you have, for example, 100 components, if rho is 0.1, it means there are 10 components that are non-zero in your true principal component, and all the others are 0. So it's the number of, is the fraction of components that are non-zero. So it's how sparse is the problem. Okay? Yeah, sure.
At the regularization term, we are penalizing what?
Basically, the idea is that when you put regularization, you are trying to penalize components that are small and should be 0 in reality. So what, maybe I erased it, but what you see from the formula, so what I had before was that J star, the fixed point, was equal to 0 when 0 when the absolute value of, when S hat times the absolute value of E hat times R is smaller than gamma. And otherwise it is non-zero. So you see, what the regularization is doing is setting to 0 things that correspond to small components of the principal component. So you are trying to suppress the noise by setting to 0 things that should be small enough, and you say, okay, let's put them to 0. And instead, when the signal is big, you try to fit it. Okay? So, okay, just to summarize what we have done. So yesterday we were looking at the problem where when you have many data and you want to extract information, so in particular the principal component, all together. So you compute the correlation matrix, you find the principal components, and you have your result. And today we are doing the same, but in a situation where you see one data point at a time, and you have to work online. So you cannot store your data. That can be true or not, depending on what you're doing. So if you cannot store your data and you only see one data point at a time, what you can do is to use this simple algorithm. Where you see a new data point, you only store the weights, j. When you see a new data point, you compute the scalar product of your weights with the new data point, and you update your weights, and then you go to the next point. And if you want, you can add a regularization. And okay, without regularization, this will converge to the principal component if eta is small enough and you wait long enough. And with regularization, you are going to converge to something sparse. And so if your principal component is sparse, you can get rid of some noise. Okay? So this is a simple way to learn principal components when you cannot store all of your data. And okay, and the message is that as a function of gamma, you can have a phase transition where for small enough gamma, you recover your signal, and if you put too strong regularization, you will go to 0, and j will be equal to 0, and you don't learn anything. Okay? Now, maybe now I wanted to show you an application of these things. So again, I have a tutorial, 2 tutorials, from always from this book, which are tutorials 3 and 6 in the book. They make use of the same data. So let's look at them. By the way, I added here some notes that I wrote to prepare the lectures in case you want to check. I mean, it's the same that is in the book, but I wrote it in a more compact way. Okay. So the tutorial 3, the goal of this tutorial was to reproduce the analysis of some data taken from these papers. These are papers from the group of Battaglia. They did recordings of some neurons in the brain of a rat. So the rat is, so what happens in the experiment is that the rat is learning a task. Okay, so you have, I don't remember all the details of the experiment, but you have a maze that is Y-shaped. So the rat starts here, and the rat has to decide to go left or right, and you train the rat. So the rat learns that, for example, on the right there is food, so it will learn after a few trials, it will learn that it's more likely to find food on the right, so it will go preferentially to the right. And what happens in this experiment is that they did the recordings during sleep, before the training. So the rat sleeps, they can put a machine, to record a few neurons in the brain. The rat sleeps, then it does the training, so it does a few times this thing and it learns something, and then they record the same neurons also during sleep after the task. So what was the goal? The goal was to see, there is this idea that when you learn something, first it is stored in the hippocampus, that is a region of the brain, and then after some time it is transferred into the prefrontal cortex. I'm not a neuroscientist, so don't ask me for details about this, but the idea is that before you transfer your memories, there is maybe some role of sleep to consolidate the memory. And what happens, and it's not clear exactly how it happens, but there is some replay. So what happens is that first, so you say you sleep before and nothing happens, then you learn something, and then some neurons during the task, some neurons will fire together. So the synapses between these neurons will be reinforced, and so you encode something, some memory. And then what happens, the idea, what they wanted to test is that after the memory is, after the task, when you sleep, the hippocampus is stimulated spontaneously, and it will replay. So the neurons that were activated during the task are reactivated during sleep, and something happens. It's not clear what happens, but there is this replay that somehow is useful to consolidate the memory. And how this happens is not clear. There is a recent work that I read that seems very interesting, where they show that if you disrupt the replay process, so they have some mice that are engineered in such a way that the replay step is, then these are like Alzheimer-induced mice, where the replay is disrupted, and they see that the memory is also disrupted. So there seems to be something important into this replay process that happens during sleep, and I think it's an open problem, but the aim of this experiment was to test if you can detect this replay, okay? And for this, they use the principal component analysis, so it's an application of what we discussed. So how does it work? What kind of, so is it, the setting more or less, is it clear? My explanation is, again, this is not really my field, so I'm trying to explain, okay. Anyways, so the data, what are the data? You have L neurons that are recorded. And in this experiment, it was 37 neurons. And these are recorded for some time. The time is of the order of 25 seconds during the task, before, during the sleep, during the task, and after the task, during the sleep, after the task. So what you get, so in the repository, you have all the recordings in the free, you have 3 files, one for each epoch. And how do they look like? This is again a raster plot of the activity. So in this plot, each vertical bar is a spike. Now, and this is time. And now it's different. So in the previous tutorial, I showed you each line was the same neuron in a repetition of the experiment. Now these are different neurons. So this is only, you have one rat, 37 neurons, one experiment. And so these are the spikes of each neuron from 1 to 37 as a function of time. So the idea is to try to identify pairs of neurons that are activated together during the task, and then try to see if the same neurons are activated together during the sleep, before and after the task, to see if there is anything that appears during the task and is reproduced during the sleep after the task that was not there before the task, okay? So how did they do that? I mean, you can do many things on this data. I will reproduce, what I want to do here is to reproduce the analysis from the paper. Then, yes?
The goals
this is not working. Should we try to, can you see? Okay. Sorry.
The tasks were to understand if there are couples of neurons that are activated at the same time during the task, during the sleep, and the third part was?
No, so sorry, you want to see if there are pairs of neurons that are co-activated during the task and that reappear co-activated after the task in the sleep, that were not co-activated before the task. So you have a pair of neurons that were not very correlated before the task, become correlated during the task. So the idea is they become correlated because you are learning something. And then after the task, they are replayed in the same way. Okay? Okay. So what they did in this, sorry, I was saying, so you can do this analysis in many ways. What they did in this, in the first paper was to use principal component analysis. Then you can do more sophisticated analysis, and there is a paper by Rémy Monasson, Simona Koch, and co-workers that does a different analysis that is maybe more detailed, but...
Devi darmi un attimo che devo...
Okay. No problem. So in the meanwhile, I can explain in the blackboard what we are going to do. So the idea is, as usual, so you have this matrix. Here you have, okay. Yeah, I'm sorry. In this case, the matrix will be transposed. So this will be our Y transpose, because in this case, it's better to consider each column as, so this will be L times M. So this will be the raster plot. You have 37 neurons, and this is time. So we are going to bin time, as we did in the previous case. This time, because they are interested, they want to have a bit more statistics in the bins, they took a bigger bin. I think it was 100 milliseconds. In the previous experiment I showed you the other day, it was 10 milliseconds. There is always a little bit of arbitrariness in the choice of these thresholds, but okay, they chose 100 milliseconds. And now, in each bin, so you have your spikes. So you can count the number of spikes in each bin. And the idea is to consider each column as a vector y. So this will be y1, y2, and you have m bins. So this will be ym. Okay, and we want to do, we want to consider these as Gaussian variables. So we want to, the assumption is that each component, so the activity of each neuron, is one variable, and these variables are taken from a multivariate Gaussian. Okay. So what we do here is we count the number of spikes in each bin. Now here you don't binarize. You say, okay, if I have 2 spikes, I put 2 here. If I have 4 spikes, it will be 4. So you have a number S that in each bin, you have a number S that goes from 0 to infinity in principle. And then from this, we want to get a variable Y. And remember that in the principal component analysis, we assumed that these were 0 mean variables. So what we do, what they did and what we will do is you compute the mean of the SI. So the mean, it means you average for each neuron, you average over the time, and you get PI, which is the mean activity of the neuron. And you can average also the fluctuations, so you get a sigma I square, which is the variance of this S. And then you define Y simply as Yi in bin B, so B is the index that goes from 1 to m, it will be just the number of spikes minus the average, and S is the number of spikes minus the average, and it is usually a good idea also to divide by the variance in such a way that in your matrix C, the diagonal elements that are the variances of the y are all equal to 1. Otherwise, if you have some neurons, you can have some neurons that are much more active than the others, and then you can have imbalances in the PCA. So you define these standardized variables that have 0 mean and unit variance that represent the activity of the neurons at each time. And so the idea is that now each column is a realization of the 37 neurons, and we want to compute the correlation to know if they are spiking together. So what you do is from the matrix Y, you compute C, that is 1 over m y transpose y. So y is m times L, and yes, so this is L times L, so this is 1 over m. So, sorry, again, Cij is going to be the average of the sum over B of yi b yj b. Okay, so you take two neurons, I and j, and you look over the duration of the experiment to the correlation between the two neurons. And then what you do is to take the principal component and see which are the neurons that are contributing to the principal component, and this should be the most correlated neurons, okay? So let's do this first. So these are the data. I mean, we skip the details, but you can also try to write your own code if you want. And these codes also are a bit old and not very well written, so I'm sure you can do better. But so the idea is you compute the matrix C, and you can diagonalize it. And when you diagonalize it, this is the result. And what you see, so I didn't really discuss it. Maybe we can do this next week, but I think you have already seen it. So if as I was saying yesterday, if the y's are pure noise, if the variables y are unit Gaussians with 0 mean and unit variance that are completely uncorrelated, then C is what I called yesterday W. So in absence of any correlations, C should be the same as W, that is X transpose X, that was where X is independent Gaussians with 0 mean and unit variance. And the spectrum of W is what is called the Marchenko-Pastur spectrum, rho of lambda. This is what I used yesterday. And it has this shape with lambda minus and lambda plus that are given by 1 plus minus square root of r square, I think, or maybe without the square, I don't remember. Let's see, is it written somewhere? Anyway, it's not, okay, it's with the square, okay. So, okay, and r is the ratio of L divided by M, okay? So what you expect if there is no signal, if it's all noise, so just the neurons are spiking independently, is the Marchenko-Pastur. And what you see here, in black, there is the Marchenko-Pastur spectrum that you expect with L, with the values of L and M that you have here. So L is equal to 37, M is, I don't remember, but something like 2000, something like this. So the spectrum is quite narrow. And what you see is that you have some eigenvalues that are much bigger than the lambda plus, which is what we discussed yesterday. If you have a strong enough signal, it will appear as an eigenvalue. Here you have more than one, but we will focus on the first one. This is one eigenvalue. In order to check that things are correct, what we also propose is that you shuffle the matrix. So if you take this matrix, and for each line you do a random permutation of the y, then you are going to destroy the correlations, right? So in that case, you should have independent variables that have zero mean and unit variance by construction. So the spectrum should be Marchenko-Pastur. And this is what you see. This is the Marchenko-Pastur, and this is the what you get from the data. Of course, it's very noisy because it's only 37 neurons, but it's close. So this eigenvalue here is really coming from some signal that you have in the data. So there is some correlation in the neurons that you can see. And this is the principal component. So here you have, so the principal component is going to be this vector E star I, that is the maximum eigenvector of C. So it has 37 components, and these are shown here. Now, if the vector was completely random, because it's a unit vector, you should expect 1 over square root of L. So the horizontal line here is 1 over square root of L. And this is what you would have if it was a random vector. So what you see is that there are some neurons that are much more represented in the principal component. In particular, these two, the neurons, these are 21 and 22, I think, that are very well represented. And then there are these other 4. So in the experiment, they said, OK, in this analysis, they said, we can suppose that these 6 neurons, 1, 9, 20, 21, 26, and 27, that correspond to these components are the ones that are contributing the most, and the rest is maybe noise. There are 2 here that are, and also these 3 here, and the rest is noise. Anyways, so what did they do now to try to compare the task with the sleep? So this analysis, I forgot to say, this analysis is done on the task. So you take the neural recordings from the task, and you compute C from the task. You compute the principal component from the task. Now, what you can do is to project the activity of the neurons during sleep, before and after the task, on the principal component. Okay? So what they did, actually, they did a bit more. They projected it on the full matrix. But then you can, so what they did is to compute this quantity here. So you compute a quantity R. R stands for replay, of time. So at each bin, at each time, you take the vector Y from the recording in the sleep, and you do sum over ij of yi of t times cij task times yj tb. Okay? They put a 1/2 for convenience, and it's important to exclude the diagonal terms because you want to really look at correlations between different neurons. So this is what they call replay. Okay, you project this. Now, if you insert, you can also disentangle the different components of C. So in particular, you can replace Cij task by sum over k of lambda k, eik, ejk. So you decompose on the projections of the different components, and if you take, for example, the principal component, here you put lambda 1 and E1, that is the principal component, you see that you get the scalar product of the activity at time t with the principal component. So so this is done here, and you can check. And this is the, okay, maybe it's better if I show it directly from the book. This is what you see. It's very noisy. I mean, biological data are always very noisy, but what you see is that this is before the task, and this is after the task. And so you see that after the task, you have much bigger spikes. So you have short intervals of time during which the neural activity is close to the ones that you had during the task. And these are what they call in the paper the replay events. So there are moments during the sleep where the same pattern, the same principal component that was present during the task is replayed. And then, okay, there is also some discussion of, I mean, sleep is not uniform. You have different phases of sleep. Again, I'm not a neuroscientist, so don't ask me for the details, but you can check the paper. And this corresponds to some particular phases of sleep during which the hippocampus is stimulated spontaneously, and you get this reactivation. So that was the result of the paper. And, okay, so you can reproduce all this analysis with the code that you have in the folder, the folder I shared with you. You can also separate the different components, but maybe we can skip this. What I wanted to show you next is what happens when you do the online learning. So this is tutorial 6. It's the same data, so it's exactly the same thing, except that instead of doing the principal component analysis offline by diagonalizing this matrix, we are going to do with the online algorithm that I discussed. Sorry. Okay, almost there. Okay, so it's the same data, and what we are going to do is to, instead of taking all the data together, we are going to take one data point at a time, and we are going to apply the algorithm I just discussed today. And I will show you directly the result. I mean, you have the notebook where you have the implementation of the, so this is the same raster plot, same data. We are going to do this in the task to identify the principal component. And so here you have this is the algorithm. It's very easy. At each step, you take one column and you update the weights. And this is what you see. So this is the, first of all, we do it without regularization, so gamma equal to 0. And what you see here is the overlap between the scalar product between the principal component that you get from the diagonalization of the matrix, so from the previous tutorial, and the one that you get from online learning, as a function of eta. So what you see is the following thing. If the learning rate is too small, so here we have finite data. So we do one pass. We start from the first and we go up to the last. So the total time, if you fix a learning rate, the total time that you can run in your algorithm is given by eta times the number of data you have. So if eta is too small, the time is too short. You don't learn. Okay? So you see that R is small. When you increase the learning rate, so this is done with one initial condition for J. I told you have to initialize J at random. So this is one initial condition. This is average over 10 initial conditions. It's just to clean up a little bit. What you see is that when you increase the learning rate, it goes up because you learn better. But you reach a point where it's close to 1. So you are learning the principal component well. But then it starts to go down. And this is because I told you that the algorithm works in the continuum limit when eta is small enough. So at some point, eta is not small enough, and you start to see the effect of the discretization. And if you keep increasing eta, at some point the algorithm will not converge and will give you an error, because basically the norm of J is going to diverge and you have instabilities. So the fact that the norm of J is conserved is only true in the limit of eta going to 0. So this shows you that when you do this online learning, you have to be careful with the learning rate. If it's too small, you don't learn because you don't use your data well enough. If it is too big, you are outside of the continuum limit. So there is a good spot here. It's around this value where you have a good learning. So you have to tune things a little bit. Okay. And this is the result. This is the principal component that you get from the offline learning, which is diagonalization of this matrix with all the data together, and from the online learning, which is the other procedure. You see it's very similar. You have a little bit of noise, but they are similar. So now, to conclude, we can look at what happens when you add the regularization, which in the online case, it's easy. You could also do it in the offline case, but it's a bit more complicated. So what you see as a function of regularization, now we are increasing regularization, is precisely this jump that I was discussing before. So you see that the overlap with the, sorry, no, this is the norm of the vector, so this is j square. And you see that j square at some point goes to 0. So when you regularize too much, you lose completely the signal. So then you can look as a function of the regularization, what happens. And what you see, so these are the components of the principal component, or I mean, the components of J, of the vector that you learn, for various values of gamma. And you see that this is the offline, the dots, sorry, maybe it's not very visible, but, well. What you see is that when you increase the regularization, some components go up. For example, these two that are big, they go up because the vector has to be normalized. And all the rest goes down. So you see that the noise is going down. And so in this way, you can try to see which are the components that are more robust, that are the last to disappear when you increase the... At some point, when you increase too much the regularization, everything will go to 0. But you can see which ones are more stable when you increase the regularization. And in this way, well, you can discuss, I mean, you can have your own opinion on the result, but you can identify some group of neurons that are the last to vanish, and they are the ones that are also more robust to noise. So you can try to refine a little bit the analysis. In the end, I mean, the dominant ones are always these two, and maybe this one, and maybe this one, okay? So then, what you can do next is to give up PCA and try instead to do what we will do next week, which is to, instead of inferring correlations, try to infer couplings between neurons, okay? And we will see that this can give you more information. But so for the moment with PCA, this is what you can do. So I stop here. You can, so I will, I stop here for this week. We will restart next Tuesday. So if you have a bit of time during these days, you can take a look at the tutorials, and if you have any questions, let me know. And so next week, we will try to conclude by discussing what you can do to, instead of inferring the C, try to work directly with the T, so with the direct interactions between variables, and try to get information from there.